For decades, construction workers have been told to keep a straight back and bend their knees. Yet manual handling injuries continue to account for more than a quarter of all reported accidents to the authorities each year. Decades of manual handling training have failed to move the needle on injury rates. Back and upper limb issues remain the leading cause of construction-related absence because building materials are consistently denser and larger than a human can safely manage alone. Musculoskeletal disorders, or MSDs, are rarely the result of a single dramatic trauma. Instead, they manifest as cumulative damage. They are the inevitable result of continual bad lifting, twisting, and stretching over months and years of a worker's career. A severe form of this cumulative damage is known as a work-related upper limb disorder, or WRULD. A WRULD is an injury to the muscles, tendons, or nerves of the arms and shoulders, directly caused by carrying out repetitive, strenuous operations over long periods, such as tying reinforcement bars or laying dense blocks. In the context of a NEBOSH exam, relying on a worker's lifting technique to prevent these injuries is a failure of risk management. If your proposed solution to a manual handling hazard is simply more training on how to lift, you will not score highly. The required hierarchy of control moves in the opposite direction. It demands engineering out hazards at the design phase, conducting rigorous, multidimensional risk assessments, and introducing strictly regulated mechanization to remove the physical burden entirely. Musculoskeletal health on a construction project relies on engineering and logistical decisions made long before a worker ever touches a load. To solve that engineering problem, we must apply ergonomics. Ergonomics is the study of how human beings interact with their working environment, machinery, and processes. It dictates that the task must be designed to fit the worker, rather than forcing the worker to contort to fit the task. The primary duty falls to the designer. Designers are uniquely positioned to assess health risks introduced by their requirements and change the details to reduce the need for long-duration, repetitive, or strenuous activity before the project even breaks ground. This diagram illustrates elimination by design. By simply specifying lighter blocks instead of traditional high-density blocks, the designer removes the need for heavy manhandling entirely, immediately reducing the biomechanical load on the bricklayer. Design also dictates mechanization. If an architect dimensions a trench specifically to accommodate the bucket size of an excavator or a remote-controlled compactor, they eliminate the need for a worker to climb down with handheld vibrating tools. Conversely, thoughtless design creates immediate hazards. Specifying service runs in cramped, low-clearance ceiling spaces forces workers into awkward, stretched positions, virtually guaranteeing strain over a long shift. The environment specified by the design also heavily influences ergonomics. Low illumination levels lead to accidents because of an inability to see properly, causing visual misperception and awkward posture adjustments during detailed inspection or assembly work. When design hazards cannot be completely eliminated, the designer must practice controlling hazards by information. They must communicate these unavoidable risks, like the need to work in a small space, to the principal contractor so it can be managed through the health and safety plan. If the physical demands on the site worker become too high, the risk management failure almost always started on the designer's drawing board. When manual handling cannot be avoided by design, the manual handling operations regulations require employers to make a suitable and sufficient assessment of the task. This diagram shows the required framework for that assessment, commonly known by the acronym LIGHT, or TILE: Load, Individual, Task, and Environment. The load quadrant evaluates magnitude alongside dimensions, surface texture, and the presence of integral handles, as a slippery surface carries far higher risk than a heavier object with a secure grip. The task quadrant scrutinizes the geometry and rhythm of the movement. High frequency, long duration, twisting, stooping, and reaching all escalate the risk profile, even if the load itself is light. The environment quadrant evaluates the space where the lift occurs. Restricted workspaces, uneven ground, and extremes of temperature compromise a worker's posture, forcing them to adopt inefficient stances that increase muscular strain. Finally, the individual quadrant looks at physical capability, age, and health. It also accounts for experience, which can actually be a hazard, as experienced workers frequently misjudge their own capabilities and overestimate their limits. In an exam setting, a critical mistake is answering a manual handling question by focusing solely on the weight of the load. Setting safe weight limits is not an effective risk management strategy in isolation. The regulatory mandate is clear. Before relying on manual effort, employers must provide equipment to avoid the hazard, automating or mechanizing the process wherever reasonably practicable. A safe lift requires perfectly aligning the worker's physical capability with the load's characteristics, the geometry of the task, and the conditions of the environment. Replacing human lifting with machinery introduces the mechanization paradox. Bringing in an excavator or a forklift eliminates the biomechanical manual handling risk, but it immediately introduces severe hazards of collision, crushing, and overturning. This diagram illustrates the core principle of a counterbalance forklift truck. The massive weight at the rear of the vehicle acts as a counterweight, pivoting on the front wheels, allowing a relatively small vehicle to lift a very heavy load safely. However, if the truck travels across an incline with the mast raised, the center of gravity moves outside the vehicle's stability triangle. Overturning is almost guaranteed. Because of these physics, strict operational rules apply. Operators must only travel with the load lowered, never turn across slopes, and site management must provide designated crossing points to separate pedestrian routeways from plant. Dumper trucks present unique vulnerabilities. Because they use pivot steering by articulating at the middle of the chassis, they are highly susceptible to overturning, especially into excavations if stop blocks are not positioned a safe distance from the edge. To mitigate this, dumpers must be fitted with ROPS, rollover protection structures. A ROPS is an A-frame built over the seat to protect the driver. Crucially, operators must be instructed to wear seatbelts so they are held safely within the roll cage if the vehicle tips. Excavators require entirely different controls. Beyond the danger of the moving articulated arms striking a worker, operators face the hazard of undercutting. This occurs when the machine digs directly beneath its own tracks, causing the ground to collapse and the machine to fall into its own excavation. Safe operation requires vital pre-start checks. A site survey must be carried out in advance to identify overhead power lines, height limitations, and underground services like gas and water pipes. The fuel powering these machines introduces secondary risks. Diesel engines expose workers to carbon monoxide fumes and fire risks, while charging battery-powered plant creates hazards from caustic acid, electrical arcing, and the buildup of highly explosive hydrogen gas. Direct supervision of every site vehicle is impossible. Therefore, the examiner expects you to prioritize controls like site layout, flat driving surfaces free of potholes, and ensuring only competent certificated operators hold the keys. Mechanization is only a valid risk control if the site environment is engineered to support the physical limits of the machinery. When plant is used to suspend a load, it falls under LOLER, the Lifting Operations and Lifting Equipment Regulations 1998. LOLER is the strict regulatory framework governing any mechanical lifting of a load in a vertical plane. The baseline requirement of LOLER is that all lifting equipment must have adequate strength and stability for the proposed use. Furthermore, every item must be clearly marked with its safe working load, or SWL, which dictates the absolute maximum mass it is legally permitted to lift. The integrity of the lift often relies entirely on the lifting accessories, the slings, shackles, and eye bolts used to connect the equipment to the load. These accessories are the most vulnerable components in the lifting operation. Material selection is critical. Chain slings are excellent for handling loads up to extremely high heat, but they are vulnerable to catastrophic failure from sudden shock loading. Synthetic web slings will not scratch delicate surfaces and absorb shock well, but they will melt and fail if exposed to high concentrations of acid. Wire rope slings fail from fatigue. Repeatedly making small radius bends causes tiny cracks in the wire strands. Over time, this structural abuse leads to bird caging, a critical defect where the wire rope strands are forcibly untwisted and spread outward, permanently destroying the sling's strength. This diagram shows a crane hook lifting a load with a two-leg sling. As the angle between the sling legs widens or flattens out from 60 degrees down to 30 degrees, the physics of rigging dictate that the tension and stress exerted on each leg increases exponentially, even though the weight of the load hasn't changed. The hardware connecting those slings must match the geometry. Dynamo eye bolts have a weak neck and must only be used for direct vertical lifts. If a sling is pulling at an angle, the collared eye bolt must be used, as the substantial neck provides the necessary strength to support the offset component. The regulations distinguish strictly between lifting materials and lifting persons. Equipment used for raising or lowering people must be specifically designed for that exact purpose. Hoists and lift cars carrying personnel require mandatory safety devices. They must have independent free fall arresters, solid interlocking doors that prevent the lift from moving if open, and edge protection to prevent crushing against the lift shaft. To verify these systems, Lohler mandates strict inspection intervals. A thorough examination by an independent, competent person must occur at least every 6 months for any equipment lifting persons, and for all lifting accessories. By contrast, equipment used solely for lifting materials, such as standard excavators or dumpers, must undergo a thorough examination at least every 12 months. A heavy lift only looks effortless on site because it is underpinned by rigorous mathematical planning, strict adherence to safe working loads, and a relentless statutory inspection regime. Safe load handling is an unbroken chain of custody. It is a systematic process, not a singular physical act performed by a worker at the moment of lifting. If the designer fails to eliminate the hazard through ergonomics and smart material specification, the manual handler on the ground is put directly at risk. If the manual handler is overwhelmed by the weight, the repetitive task, or the restricted environment, the light factors, then mechanization must be deployed. This flowchart shows the precise chain of custody. Deploying mechanization without strict Lohler compliance and thorough examinations results in catastrophic failure. In exams, follow this path. Prove you understand elimination by design and mechanization before mentioning worker training or personal protective equipment. When presented with a load handling scenario, you must evaluate the geometry of the task, the constraints of the environment, and the physical limitations of the equipment simultaneously. Mastering Element 8 means seeing beyond human muscle. It means understanding the complex engineering, physics, and regulatory systems that keep construction workers safe.